Hello, this topic is getting ready to solve bigger equations, looking at them as functions. And by a function in engineering, what we mean is you have an input and you have an output, and in between something happens. If that input turns into something else and you get an output. In math, pretty much means you put in some number x on the horizontal axis, and then you see or you can calculate what value of y or the vertical axis. In engineering, it might be that you put in a certain amount of coal to heat up your steam, and it goes through a great big power plant, and what comes out on the other side is electricity. So there are lots of different scales, I guess I would say, of functions, but all of them are modelable by math and by science. So there are 4 different ways to represent functions. The first way is with words, and those are, the dreaded word problems. But, of course, it makes the most sense that where we're going to start if we're going to use math is with a description that's verbal. So, for example, with words, let's say we have a ball that's thrown up, that we're standing 3 meters above the ground to begin with. It's thrown up from there with a velocity of 14 meters per second. How far above the ground is that ball versus time? Like maybe starting at time 0. We can also represent that algebraically. So we can turn those words into an algebraic expression or equation or formula. And in this case, it's that the height of the ball, how far it is above the ground, is equal to 3 plus 14t minus 5t squared. And you get that equation using the velocity and the acceleration in physics. I didn't want to go through that here, but it's not too hard to do. You can also represent it numerically. So you could just have a table of values. And so here's a table of values. So if our input at time, interesting that I put time equals minus 0.2. Does it make sense to have time before 0? It actually doesn't. But because we have an algebraic expression, if we don't say time starts at 0, this is going to give us a quadratic and it would go backwards. But anyway, if I actually could manipulate time and go back to t equals minus 0.2 seconds, I can figure out the height at that point is 0. If my input is z is 0, so at time 0, this is when I'm throwing the ball up. I do expect it to be at a height of 3 meters because that's where I said I was. And indeed, when you put in time 0, you get 3. So if I put in time t equals 1 second, so 1 second from when I threw that ball up and the velocity was 14 meters per second, I'll find that the height is equal to 12 meters. The last way, the 4th way I can represent is graphically. It's one of my favorite ways. And so here is the graphical representation of this algebraic equation, which is h equals 3 plus 14t minus 5t squared, right here. And it, of course, matches our table, and it matches our words. So all 4 of these represent the same basic modeling. So we can do it graphically, numerically, algebraically, or with words. And this is really useful. It's useful to be able to go back and forth. And as you get further and up into higher math, you get to the point where you just graph things in a very general way without doing all the details, because you can tell a lot about how functions work from looking at their graph or their picture. Same thing with an algebraic equation.